Welcome to the third and final segment of our Investigating Charges session on electrostatics. Now we want to look at what exactly it means, when we say that charge is quantized. We've already, just to take you back from the first segment, we said that the subatomic particles, which are electrons and protons, are exactly what contributes to the type or nature of a charge that a material has. Right. Now, having said that, so we want to focus on what we refer to as quantization of charge. Let's start that with a discussion which says that two charged objects are attracted to each other and touch. Predict what happens next. Right. Now, we've got two objects, all right? Let's call this one Q1, okay? Let's call this one Q2, right? Now, already they're at a distance apart. It means that Q1 exerts an electrostatic force on Q2 and vice versa, right? But now you must also think about the forces in terms of the vectors. The force by Q1 on Q2 is actually towards Q1, while the force on Q2 by Q1 is actually in the other direction. So the direction in terms of vectors is very important. Now, if we bring them into contact, okay, what exactly happens? Charge is going to be distributed. So touching is actually a physical process, right? Okay, so touching is actually an example of what we call a physical process. What do we mean? They come into contact with each other. And as long as these two materials are conductors, right? So conductors, remember physical properties, are materials that actually allow charge to move or to be transferred between those materials. So we refer to them as the conductors. So this one is +2 nanocoulombs, and this other one is -5 nanocoulombs. Now, in terms of measurement, in terms of magnitude of quantities, in science, units are a very important or critical component, because when we do problem solving or calculations, that is, we need to pay careful attention to the SI unit. So the conversions are very important. Just to get that out of the way, we know that for argument's sake, when we have got 1 millicoulomb, for argument's sake, this is equals to 1 times 10 exponent -3 coulombs. So this is like 1,000th of a coulomb. While we have got 1 microcoulomb, this is 1 times 10 exponent -6 coulomb. This is like a millionth of a coulomb. It's a fraction. So these are smaller units. And then we get to the nanocoulomb. 1 nanocoulomb is equals to 1 times 10 exponent -9 coulomb. And then we usually also deal with picocoulombs, which is 1 times 10 exponent -12 coulombs. So this should be very clear from the onset in terms of units. Right. And then now if the two come into contact, that's the physical processes, we know that electrons are transferred. Right. Let's break it down. What exactly do we mean when we say electrons are transferred? If we have got Q1 and Q2, if Q1, for argument's sake, loses, okay, whatever is lost by Q1 equals what is gained by Q2, all right? So what is lost is equals to what is gained is also equals to what is actually transferred during that contact or the physical properties that we earlier referred to, right? So the transfer of electrons occurs. But here, it's very important, if we can quickly go back to that, Q1 is positive. What does it mean? Q1 has more protons. This one has got excess protons, right? Okay, so this one has got excess protons than electrons, while Q2 has got excess electrons. Just take that into consideration. So meaning that for Q2, there are more electrons than protons, right? Okay, having said that, so the Q2 is more negative, while Q1 is more positive. So this one is more negative, okay, more negative, while Q1 is more positive, right? So if the transfer of electrons occurs, it is actually from Q2 to Q1, right? this is what we mean when we say electrons are transferred. But also let's take into account that the transfer is actually from Q2 to Q1, okay, in that order, as the arrow suggests, right? And then once these two are actually in contact with each other, charge will be equally distributed. So we've got what we call the net charge, which is the Q net. So the word net is very, very important in physics, because we are going to use this word many instances when we talk about the net force. We've spoken about the net electrostatic force, for argument's sake, when we started our first segment. But now we're talking about the net charge. Now, the net charge is the total. So the word total is in other words, would say net or resultant. But in this case, we're talking about the total charge, which is Q1 plus Q2, right? Q1 plus Q2, that's our net charge, meaning that this is, if we can go back quickly, just to verify that, Q1 is positive 2 nanocoulombs, and the other one is negative 5 nanocoulombs, right? So if we talk about the net charge, is 2 nanocoulombs, which is positive, plus negative 5 nanocoulombs. So the net charge in this system therefore becomes a negative 3 nanocoulombs, right? Now you'd realize that after the charge has been equally distributed due to the contact, what exactly happens? Still, after contact, after this physical process, Q net is still negative 3 nanocoulombs, which is from negative 1.5 plus negative 1.5 nanocoulombs. And then I want also to draw your attention to the nature of the force that exists between them. Initially, they were oppositely charged, then they were attracting each other. While they've got the same amount of charge, now after the charge has been distributed, they experience a force of repulsion, because now they are like charges, both of them are negative. Now, the new charge that each one of them attains as a result of the contact process, of the process of coming together into contact, which is a physical process, we're saying it's equals to Q net, which is the total, divided by 2. Why do we divide by 2? It's because this charge is equally distributed. Then we'll get negative 3 nanocoulombs divided by 2. Then the new charge in each one of them, which is the same for both, is actually equals to negative 1.5 nanocoulombs, which is exactly that, right? So that's the thinking. So when two materials are brought into contact, charge is equally distributed, but we must also note that the net charge before they brought into contact and separate is equals to the net charge even after they were separated from each other, right? Okay, so what charge was transferred? Okay, now we're talking about the charge which was transferred. Now, the main thing here is we need to arrive at a point where we are able to say, okay, indeed, charge is quantized in terms of the electrons that are lost by, Q2, which is the same number of electrons that are gained by Q1, as is the case here. And also, that is equals to the number of electrons that are transferred between these two materials, Q1 and Q2. Now, the follow-up question says, what charge was transferred? Now, the transfer obviously occurred between Q1 and Q2. Now, we also need to realize, as we've already mentioned, that the net charge remains constant. We still have a Q net of negative 3 nanocoulombs, okay? So the net charge is still the same, but the charge has now been equally distributed. So it says what charge was transferred. Now we're actually talking about the change in charge. It could be for Q1. Let's see, we know that change in science is actually equals to final minus initial charge. So the final charge is actually the new charge, right? In this case, the new charge, if we consider Q1, that is negative 1.5 nanocoulombs minus the initial one, which was actually plus 2 nanocoulombs, okay? Plus 2, okay? So in this case, this gives us negative 3.5 nanocoulombs. So charge 1 became more negative by negative 3.9 coulombs. In other words, the change in its charge was by magnitude negative 3.5 nanocoulombs. This was the gain. Now let's look at the change for Q2. Okay, still we're saying Q final, which is our Q new, minus the initial charge before they were brought into contact. Now the final is negative 1.5, which is the same as the final charge for Q1, okay, minus the initial one was actually negative 5, right? So it's negative 5 nanocoulombs. So if you simplify that, it will give you negative 1.5 plus 5, which gives you actually positive 3.5 nanocoulombs. So delta Q2 is equals to positive 3.5 nanocoulombs. What does that mean? It means this one lost, or it became more positive. And when you compare the change of charge of Q1 versus that of Q2 is of the same magnitude, just that one became more negative by gaining, while the other one became more positive by losing, right? And then the other question says how many electrons were transferred. Now we want the number of electrons. This brings us to our, the main concept in as far as the quantization of charge. So when these two materials are actually brought into contact, what are we saying? We are saying the Q2, because it has got excess electrons, a certain whole number of electrons are actually transferred from Q2 to Q1, as was the case here. So we know that the principle says that every charge in the universe is a scalar multiple of the charge of a single electron, right? So this E is actually the elementary charge, which is given in this case. So every electron has got that charge. So this principle, what it says to us, every charge that exists is actually in multiples of this number. So this is a constant, which is the charge of a single electron. So if we can talk about Q1 for argument's sake, the number of electrons that Q1 actually gained. So if we would say to us, what's the new charge for Q1? That new charge is negative 1.5, okay, times 10 exponent negative 9. Why are we doing that? Because the elementary charge is in coulombs, while the charge of Q1 is in nanocoulombs, okay? So take note of that. So we want the number of electrons, so this is multiplied by negative 1.6 times 10 exponent negative 19, right? So if we want to find the number of electrons that were transferred, we'll make that the subject, okay? So if that's the case, then we'll get negative 1.5 times 10 exponent negative 9 divided by negative 1.6 times 10 exponent negative 19, right? So we can then go to our calculator. What is also important is that the number of electrons transferred cannot be negative, okay? So it's a positive, or an integer number of electrons. We can have 10 electrons for argument's sake, but we cannot have minus 10. So when I do that division, the signs must actually be the same. So if we go to our calculator, we would actually get to a point where we say, okay, that's the division there, which is negative. Take note of the negative that we used, negative 1.5 times 10 exponent negative 9. We divide that by negative 1.6, okay, multiplied by 10 exponent negative 19, right? So that's the calculation there. So how many electrons? That's a very big number. This is like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.375, right? 9, okay. If we can just go back quickly to that, 9.375 times 10. We need to go back because we want to write it in simple scientific notation there. So we've got how many zeros here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's times 10 exponent positive 9 electrons. So this does not have a unit because it's just the number of electrons. So when you do the same calculation based on the number of electrons lost by Q2, you'd actually get the same because the number of electrons lost is equals to number of electrons gained, right? So that, having said that, it takes us to, the summary as an overview, okay? We recognize and appreciate that all matter consists of atoms, okay, which has got the same number of positive provided it's neutral, okay? And then charge cannot be destroyed or created. This leads us to the principle of conservation of charge, which tells us that the net charge in a closed system remains constant. And it's only the electrons that are transferred when there is contact during any physical process, as explained by the law of conservation of energy. And all electrons have got the same charge, which is a constant, negative 1,6 times 10 exponent negative 19 coulombs. So this is a physical constant. Having said that, I think there's quite a lot we've managed to discuss during the course of today's session, but the main thing is about conservation of charge, how point charges interact with each other, and ultimately the fact that charge is actually quantized. Having said that, I think we've reached the end of our session. From myself, Themba Ncube, is cheers and bye-bye for now.